All right. Next, let's revisit the definition of congruent triangles. So at the very beginning of 5.5, we talked about what does it mean for two triangles to be congruent. Actually, no. I'm going to call this triangle MAC for Megan and Connor. If you want to do your own initials, you can totally, if there are three, then you can totally do your own initials. So I'm teaching you how to prove triangles are congruent, right? And the definition of congruent triangles is that all corresponding parts are equal. All corresponding side lengths are equal. All corresponding angle measurements are equal. It doesn't matter what orientation these triangles are in. As long as all of their parts are equal, then they must be congruent. Now, what we've learned is there are 5 shortcuts to prove that two triangles are equal. We don't have to prove every single piece is equal. We only have to prove these 3 things about triangles, and then we can prove, therefore, that they are equal. But a lot of times that's not the end point for our proof. A lot of times the end point for our proof is afterwards. We tend to prove that triangles are congruent, and then from there move on and try and prove something else. Maybe we're trying to prove that lines are parallel, or maybe we're trying to prove that lines are perpendicular, or like something else is going on that we're using the fact that these two triangles are congruent to then find something else. And how we do that is we use something that's called CPCTC, or corresponding parts of congruent triangles are congruent. All this means corresponding parts, right? So parts that match up, right? So their corresponding side lengths or their corresponding angles. So corresponding parts of triangles that are congruent. So once you've proven that triangles are congruent, then you can say that their corresponding parts are also congruent, right? It's just the definition of what it means for a triangle to be congruent, but we don't write definition of congruent. We write corresponding parts of congruent triangles are congruent, or CPCTC. So just like we've labeled up above with our triangle reasons, where I'm like, okay, first you have to state these 3 things, and then you can say this because of HL, right? So here below, we're going to do the same thing. Here, we're going to say first you need to state in your proof, or say in your proof, triangle ABC is congruent to triangle A prime, B prime, C prime. And then you can state all of the following things. You can state that angle A equals angle A prime, angle B equals angle B prime, angle C equals angle C prime. You can also say that AB is equal to A prime, B prime. BC is equal to B prime, C prime. And AC is equal to A prime, C prime. And that is all because of CPCTC. This is a great, great reason. And if your final proof statement is not prove that these triangles are equal, you're probably proving that these triangles are equal and then moving on using CPCTC. CPCTC can only come after saying that triangles are congruent. You cannot use them to prove that triangles are equal. You also cannot use it before you've proven that triangles are equal. So first comes proving the triangles are equal, and afterwards, only afterwards, comes CPCTC. Very common mistake. Don't be that student. All right. We're jumping head first into proofs again. So we are given that angle T is equal to angle Q. This is actually an IXL example that I really liked. I hope that you guys are taking advantage of IXL and using it to practice because it is really great. Angle T is equal to angle Q, angle S is equal to angle V, and then we're given that SR equals UV. Realize SR is only this segment, right? And UV is only that segment. So we're not even talking about a whole side length of a triangle here. We're talking about a part of a side length of a triangle, which is difficult because we need to say that the whole side length is equal to the whole side length. So we're going to use segment addition to try and talk about the whole side length. We know about a part. We want to talk about the whole. So in order to bridge those guys together, in order to go into the next room, we need to talk about segment addition and put them in an equation together. When you put something in an equation with something else, then you're bridging a gap. You're talking about them together, which will lead you from one path to the next. So I've got some ideas going, and now what I'm going to do is I'm going to write them down. But I know I need to write my givens. I always run out of space. Okay, so I have the two angles and I'm starting to realize, well, I need a side of some kind in order to then be able to move on. And if I don't have that side, I need to build it up. And I know I'm talking about a part of a side, so I want to talk about the whole side in order to be able to finish my my statement. So first I'm going to do some segment addition. I'm going to say SR plus RU equals SU. So I'm talking about the whole side length of SU, and I'm going to do VU plus RU equals VR. I want to prove that SU and VR are equal to each other, which means I need them to be in the same sentence, the same equation. And in order to do that, I need to create a relationship between them, and I don't have that yet. What I do have is that RU is in both of them, which is nice. And I do know that SR and VU are equal. It's been given to me. So I'm going to do what we did earlier on when we were talking about the angles of a triangle and substituting just one piece out. I'm going to take out SR from that first equation and replace it with VU. So instead of SR, I'm going to write VU. But besides that, I'm going to write that entire first equation the exact same way. So instead of SR, I wrote VU, but now I'm going to say plus RU equals SU. All I've done was taken that first equation and take out SR and replace it with VU, which is just substitution because it was just one piece. Sorry about not writing the statement before. The statement before was segment addition. Now, once I've done that, go back to the equations, right? Where all we're doing is we're trying to manipulate these equations in order to be able to prove something that we want to prove in the diagram. Notice that I have VU plus RU is equal to VR, and it's equal to SU. So I've got one whole side or one whole half of an equation that's the same, and they're equal to different things, meaning that those different things, if they're equal to the same thing, must then be equal to each other. So I'm going to take out one whole half of the equation. I'm going to replace VU plus RU with SU. So I'm going to take the second equation right here, this guy, and I'm going to say, instead of VU plus RU, I'm going to say SU equals, and then finish the equation, VR. And that is my transitive property of equality. Okay, now I've stated that those whole side lengths are equal to each other. Sometimes when we start to have overlapping triangles, you're going to see as things get more complicated, that they're a little bit harder to use like your tick marks and keep track of what's going on. Sometimes, maybe not now, but it might later. You're always welcome to just do like a poor man's sketch of the triangles over here and make sure you label your pieces. So you know what's going on. But those are the two triangles just separated out. And I know I want to prove that they're equal. And I was given that that angle was equal to that angle. And then I was given that that angle, whoops, there we go, was equal to that angle, right? V and S and T and Q. And then now I just proved that this side length is equal to this side length. Now maybe a little bit clearer to see, oh, I've got an angle and an angle, but not the side between them. So that must be angle, angle, side. I think it was triangle STU and VQR. Are congruent because of angle, angle, side, Q, E, D. And we're done.